Hello, thank you for coming to my talk. I'm Hayden Frye, and I'll be presenting research on transition sum rules in the no-core shell model. So atomic nuclei exhibit discrete energy states governed by the laws of quantum mechanics, and then transitions between states are governed by fundamental forces. And so here I give two examples of electromagnetic forces as well as the weak nuclear force. And so along with being important for understanding nuclear structure, the study of transitions has applications in astrophysics as well as applied and fundamental physics. And so to give an example of kind of what calculations we do, we solve the many-body Schrodinger equation given some Hamiltonian operator. And so an example of a Hamiltonian operator we use is shown here, where we have a kinetic energy term as well as a series of n-body terms. For our studies, we only go with as far as the two-body term, and we exclude the three-body term as shown here. And so we then expand our A-body wave function in terms of anti-symmetrized many product wave functions called Slater determinants, made up themselves of single particle wave functions. And finally, this allows us to solve the Schrodinger equation by diagonalizing a matrix eigenvalue problem, one where we can solve it directly using computers for a given number of states. And so for our study, we use this no-core shell model, an ab initio model, meaning that it uses underlying physics to describe nuclear structure. Specifically, we use something called the chiral effective field theory, where our interactions are derived from leading order terms in a perturbative expansion. So basically, this gives us our two-body interactive forces that we can plug into our Hamiltonian, then we can solve our Schrodinger equation with that. Additionally, however, no-core shell model also uses a basis of harmonic oscillator wave functions. It's for the single particle wave functions, and it also adds a center of mass term to the Hamiltonian. And so this then gives us our expansion in terms of our harmonic oscillator wave functions. Where here M max is the number of allowed harmonic oscillator quanta excitations in our model space. So essentially, as M max goes to infinity, our calculations converge to exact. And so what we want to do is compute transition sum rules using the no-core shell model. And so a sum rule comes from something called a string function. A string function is simply just the probability amplitude of a transition occurring between initial and final state. And so we have our discrete energy basis here, and then the sum rules or the string functions themselves show fairly smooth behavior. And so the sum rules are essentially just the energy weighted sums of the string functions for a moment k. And we can write our sum rules as expectation values with respect to initial states. And then using these expectation values, we can plug them directly into existing nuclear shell model codes for a given range of nuclear energy levels. So to give a few notable results, we compute sum rules for a variety of common transition operators. So we compute them for what are called electromagnetic multipole operators, as well as charge-changing Gamow-Teller operators governed by the weak nuclear force. And those had to do with beta decay. And so we compare results against well-known results. So right here, we show that the Brink-Axel hypothesis, which states that non-energy weighted sum rules are independent of initial energies. And that's essentially what we see for our results, given our limited calculation space. And then we also compare results to the Thomas-Ricci-Kuhn sum rule, which gives a prediction for the E1 energy-weighted sum rule. And here we see an enhancement factor kappa. So we compare our results for our E1 energy-weighted sum rules against the bare TRK sum rule, where kappa equals 0. And the differences between the two indicate momentum and non-local behavior. So non-local behavior and a momentum dependence on the interactions we used. So we could take this and use, for example, other interactions to compare the non-local behaviors of such interactions used in these calculations. Thank you, and I'll look forward to seeing you at ACSESS.